All right. Hello, everyone. I'm Sayna from UC Berkeley, and today I'm going to talk about our work on remembering for the right reasons, or RCUBE. It's a work at intersection of XAI and continual learning. And these are my wonderful collaborators. We're all from UC Berkeley, except for Marcus, who works at Facebook AI Research. All right. I don't think I need to explain what continual learning is for this group, fortunately, and you're all aware of the objectives and the difficulties that we face in this research. And I'm sure you're aware of this slide as well. These are roughly the three categories of continual learning literature, and main concern being is catastrophic forgetting. So these are the three approaches to tackle that. And the method that I'm going to talk about to you today is a kind of combination of regularization-based and memory-based methods. And by that, I mean model distillation and experience replay. So I'm going to talk about those. But before that, let me just explain what experience replay does before we get into RCUBE. So in experience replay, raw samples from each task are kept into so-called a replay buffer, and the model can revisit them as it learns new tasks. And knowing how much explanations in general can help humans remember, we wanted to explore this, that how can we leverage model explanations to enhance the experience replay process for a model. So here is what we propose. In addition to the samples, we propose to also store the predicted model explanations for them as well. And the goal is that we not only want the model to remember its decisions for prior samples, we also want it to remember where in the image it paid attention when it was making those decisions. Basically, we want to ensure the model has the right reason, quote unquote, for its predictions by encouraging it to remain consistent with the explanation that it used to make decisions at training time. So to be specific, use saliency map for explanations. And these are the three saliency maps techniques that we looked into. And yeah, and these the reason for choosing these saliency map techniques was that they all have passed some sanity checks. I refer to the NIPS paper that is called sanity checks for saliency papers. Depending on the data and the model size, some saliency maps do make sense and some not. So we try to stick to those that they do make sense. And here's the only trick in this paper is this objective function that is added to the regular loss, and that is just we put a L1 loss on the explanations of the model, and for that XAI thing we use this three saliency maps. Any questions? Because that's basically it. Okay, so I'm going to show you some boring results before getting to more interesting results. So in order to make sure that the saliency maps we are computing are not some artifacts of the architecture, we tried different architectures. And so basically at a very high level, saliency map is a weighted linear combination of feature maps up to a certain point of your choice. It's often the last layer of the convolutional part of your network, and yeah, different architectures will give you different feature maps, and they differ in size. So we tried these three networks, ResNet, AlexNet, SqueezeNet, and we tried the three saliency map techniques that I talked about. So among the three of them, GradCam gives you the smallest saliency map size. It's equal to the kernel size of that convolutional layer that we choose to stop at. And so it's that small. SmoothGrad and backprop, they both give you same size as your image. They're just the gradients. Smooth grad is just a smooth version of the gradient with added some noise. And GradCam is a weighted linear combination of all the feature maps up to that target layer of your choice. So as you can see on this plot, for every layer, for every solid line, there is a dot line. The dot line is without. Let me check which one is this. Oh, okay, yeah. The dot line is without the saliency map technique added to it, and the solid line is when it is with RRR loss or RQ loss. And consistently, it improves the experience replay on all the three architectures that we tried, and using all the three saliency maps. So we went with the saliency map that was the more memory efficient, which is GradCam, because of the small map size that it gives you. On the right-hand side, so both of these, sorry, I forgot to mention, both of these are few-shot class incremental learning on COP, 10-way 5-shot, and they're being done in 11 tasks per task. First task is the base classes, 100 classes, and the remaining 10 tasks are the remaining 100 classes. So these are the methods that we tried to add RQ on top of them. So let me just, if you haven't already noticed this is not a standalone method, or this is not one of those papers that we tried to become state of the art or something. We wanted to introduce a new perspective into looking at, okay, what can we also get out of these samples that we are storing into the memory? How can we enhance them? And what is it there that is making this improvement in performance when this like small map is also stored into the memory associated with every image that you choose to keep. So so RCube is not a standalone method. We added it to existing approaches by just adding this loss to their objective function. And these are the so-called state-of-the-art methods for few-shot class incremental learning. And this is when RCube is added to them. So the solid line is when the RCube is added to each method of the same color. And the joint training is the black line here. And that's like an upper bound, not continual learning, but upper bound. So you can see that it reduces the gap between the best acting method, which is topic, and it just reduces the gap between that performance when RCube is added to it. All right. We also looked at regular class incremental learning, not just few shots, so many shot as opposed to few shot. And we looked at CFAR and ImageNet. On the left side CFAR, right side ImageNet in 10 tasks, CFAR in 20. And again, consistently boost the performance for any method. For CFAR 100, the boost is not that significant. And we think it's because of the saliency map for images of 32 by 32 in CFAR. It's just a 3 by 3 matrix. So it's not a huge compressed version of the image, because to begin with, it's a small image. But in ImageNet, which we use 224 by 224 image sizes, the boost is quite more visible, and that's because the images have already good resolution, and their saliency map is larger than the 32 by 32. So for ImageNet, it's 7 by 7. For 32 by 32 in ResNet 18, it's 3 by 3. It depends on your input size and the target layer that you're choosing in the architecture of your choice. So again, consistently, it boosts the performance for regular class incremental learning. All right, so those were the boring results, but let's get into some more interesting results. So we tried to see how explanations predicted by a model would be different with and without RQ. So for this, we did a couple of experiments. First, the use pointing game experiment. If you're not familiar with it, it's a simple experiment to evaluate how often a model is pointing at the right evidence or object for its predictions. So we use the COP dataset for this because we had segmentation annotations for them, even though they're weak annotations, but they serve the purpose. So we use the ground truth segmentation annotations to make sure that the peak of the saliency, the predicted saliency map, falls inside the object region. And we saw that RQ always makes the model to be better at this point in game, both at the beginning, right at the end of a task, and as well as all the way at the end of the sequence. So I use the regular accuracy, average accuracy, and backward transfer on this hits and misses. That's what we call a hit. Is when this red cross is not inside the segmentation mask, and this is a hit, and then otherwise is a miss. And so the number of times that it happens to be inside the segmentation mask versus the number of at the end of the task versus at the end of the sequence, I calculated the backward transfer for that to show how much it forgets of being inside the segmentation mask. And for experience replay and topic, here is how both the metrics get better. So any questions up to this point? All right, sorry. So those are, you're familiar with these already. Okay, we also did a second analysis. So ideally, we want our model to predict an object correctly only if it is looking at the correct region in the picture. But not only that, we also do not want it to predict an object correctly if it is not looking at the right evidence for it. So for making sure those are happening, we use precision and recall, and with and without RQ, of course. And then we saw that RQ caused both precision and recall to improve across different methods. Here we are showing, again, experience replay and topic for COP dataset. Yeah, numbers are shown here, but what matters is that both precision and recall are improved, and that shows that it's not just about a few percentage of accuracy increase. It is also making the model more explainable and finding the right evidence in the picture. And here we looked at some visualization of the saliency maps across tasks, again for the COP experiment few shot. And this is an example from the test set, of task 2, so after learning the base classes. Top row, you see the experience replay, and the bottom row, you see experience replay plus RQ. We see that without RQ, the model makes an incorrect prediction for the sample at the end of task 7 and never recovers from it. So it keeps predicting wrong prediction as well as a messy saliency map. But the bottom row, you see that the model makes a mistake after task 5, but it's able to recover itself and again produces a saliency map. It happens to be that as soon as it corrects its prediction, it is also generating a saliency map similar to what it produced after task 2. All right, so the conclusion was that this is a new way of looking at continual learning, regularization-based approaches that try to distill the model, the feature maps. This is what you can. This is a way to get more out of the samples that you have chosen to store. Well, we are not saying that memory-based methods are the best or anything, but if you already chose to store samples, it's easy to store their saliency maps associated with them and get a better performance and a better rationality in the predictions that you're making. And yeah, we wanted to advocate for XAI that it can be used as a tool in this field to improve the performance and make the model both more accurate and more interpretable. And yeah, and here is the link to the paper. I can take any questions that you have.
Thank you so much, Sayna, for your very interesting presentation. When I've seen this paper out, I thought it was very interesting, and so that's why I invited you. And thank you so much for joining us today.
Thank you for inviting.
So maybe I can start. Yeah, maybe I can start with a question. So you said that this saliency information is can be essentially encoded in a feature map in the higher levels of the network, right?
Mm-hmm.
Okay, so it's a rather let's say small data that you can store with the, let's say, raw input images, right? And then you use some kind of distillation or regularization to make sure that you're not changing that so much, right, over time. So I was interested in trying to understand if you somehow had some thoughts about the relationships between these techniques and applying, let's say, distillation techniques that is not applied at the end, let's say, on the logits or the output layer, but also in the middle of the network. So if there are some relationships with your technique, and I mean, if this technique maybe can be somehow part of a larger set of methods that do distillations at in the middle of the network for features in the network.
I see. That's a very good question. Yes, so the connection between this work and distillation on the approaches is that, at least from what I have seen, distillations happen at like specific layers of a network. I've never seen that a distillation model takes like a combination of different layers. So this work, just because of the definition of how saliency maps are computed, at least the GradCam method, it's you have to basically always find that linear combination for all your feature maps for those samples that you chose to store into the memory. So your model has to always come up with some sort of similar saliency map to make sure this loss is being minimized, but it still has some freedom for the parameters. There's still freedom for them to change in favor of learning new tasks, while still preserving the saliency map that has to be generated for those samples in the memory. So this is a little bit of a less restriction compared to if you put a loss on just like one feature map and always trying to get the same output of this layer. This layer always will be the bottleneck. But when a combination of them have to come up with like an outcome, then each can adjust. So that's the connection. We tried this method on, if you looked at my results, we tried this method on LWF and EWC. So LWF is model distillation, yeah. And in those methods, we did not use examples stored in the memory as a replay buffer. I mean, there was no experience to replay, just because by definition, they don't have such a thing. And those experiments show the effect of this loss without using the training images on a model. So that also shows how it can improve a model that is already doing model distillation, like LWF. Yeah. So did that answer?
I see.
Your
Yes. Thanks. Thanks. So do you argue that this method can be applied to any visual problem, or maybe also outside the context of vision? Maybe interesting to
see. Usually explainable AI has been tackling visual data. If there is XAI technique that can be applied on a regression problem. First of all, this is just classification because GradCam is only defined for classification. If there is a saliency technique that works for regression or works for something other than convolutional networks, because this also requires to have a content and you have an image and it's a classification. But if there is a saliency technique, there will be a saliency technique that can deal with other than visual data. Yeah, sure. Because basically, mathematically, it's just a combination of feature maps, but it has a meaning behind because of the XAI component. But one thing that I also wanted to add is that this is there has to be, just like any other regularization-based method, there's also a limit to this. Maybe for experience replay only, if you choose to keep all the samples, that would be your joint training, that would be your upper bound. You always get a better performance. But with having this R cube added to it, that might not happen. I haven't tested it, but I can assume that there is a limit to every model. If you keep your model capacity fixed, then putting this loss on more samples will restrict you from learning new tasks. If you want to preserve the saliency map for all your samples, you're not going to learn anything new. So so there is a limit for the number of samples. I didn't look into it, but because with the data sets that exist as benchmarks, there's always a network that we all know that will not run out of capacity. ResNet 18, even on ImageNet, you always have the capacity to learn it.
I see, thanks. So there are a few more questions in the chat. Do you want me to read it, or maybe you want to read it yourself?
Yes, please. I'm not looking at the chat. I'm not used to this platform. Seems like
no problem.
People use MSD.
It's quite stable, and we have it for free in our university.
Yeah, so I liked it. Yeah, it was just my first.
Oh, okay. Nice. So you, okay. So you should be able to see the chat. I don't know which version you are using, but for me, it's in the top bar.
Yeah, I'm seeing 3 questions. So first is how more computationally expensive is storing the maps along the examples? Also, is the code freely available? Okay, so with GradCam, with image, it depends on the model architecture that you choose and the input size. So I'm giving you an example that I did for ImageNet 224 by 224 images. With ResNet 18, it's a feature map of 7 by 7 for every image. So compared to the memory that an image would take, 224 by 224 times 3, it will be just a 7 by 7 saliency map. So it's almost negligible. The code, yes, I attached it to the, never mind. Yes, it will be on GitHub soon. Okay, how much can you trust saliency maps, for example? Okay, yeah, that's a good question. How much can we trust them? We also want to make a note that we really, I didn't cherry pick the examples that I wanted to store into the memory. Those are randomly chosen. Some of them might have been predicted wrong. Some of them might have been predicted correctly. I don't know. And I didn't check for it. The goal is the model remembers its decision, whatever it was, wrong or correct.
Yeah.
If you get the same performance, you will not have a forgetting. That's like by definition. So that's a good thing about it, because there is a lot of debate on how accurate saliency maps are and how reliable they are. There's a whole argument in the community. I'm not from that community, but I've heard it from them. So here, the good thing about this method is that it really doesn't matter how good the saliency maps are. It's just that you want to preserve them. You want the model to do the same thing that it did in the first place. So saliency might focus on generic things like things. In this case, saliency might be determinant. Yeah, I guess I answered that question. Let me know if I didn't answer that question. Why not also use calibration metric Additionally, salience map doesn't show calibration. Accuracy confident. I'm not sure if I'm getting what calibration metric is. How do you want to calibrate things, and what is it there that you want to calibrate?
And of course, you can, if you want, to switch on your mic and clarify your question or clarify it in the chat as well.
I think it is related to my previous answer on it really doesn't matter how accurate the saliency maps are. All we want is to just get the same thing. And I'm sure for some samples, I mean, for a harder example, some samples were predicted wrong, and I just wanted to preserve that. Accuracy of the classification. Oh, confidence of prediction. Okay. I still don't get the relevance of calibrating my probabilities for computing the GradCam. You mean the GradCam saliency map?
Or maybe I mean, he wants to say that we should somehow calibrate. I mean, I don't want to use this word now. Just enforce maybe the regularization on maps, on saliency maps that are correct, and give more freedom on those maps that are not correct, or something like that.
I see. It's okay.
It's difficult to do without, run through labels. So I don't know.
Well, I assume calibration should always help because, yeah, GradCam's directly using the logits, and the more calibrated they are, ROI, well, it doesn't say how confident it is on the prediction. Sure, calibration. So, yeah, I agree with you. Calibrating those logits would theoretically should give you a better saliency map, at least more focused on the object with a more pronounced peak at the saliency map. That's what I also assume that it should be the case. Yeah, I didn't calibrate the probabilities though, but I agree with you. It should help.
All right. Do we have any more questions for Sayna?
Hi. I have a question, or rather two. The first one is related to this trust in the saliency maps. Like, did you also try your experiments where you had a base, like you didn't pre-train on 100 classes? Did you try from scratch, and did it still work if you did so?
For which experiment? For which data set?
I think you had one where you start with 100 classes and add more, right?
Yeah, that's the few shot case. You always learn a bunch of base classes and then incrementally learn few classes at a time with few shots. Yes, I used the pre-trained on ImageNet, if I'm remembering correctly. For COP, yes. But again, it's going back to the same explanation for saliency map. Don't need to be perfect, don't need to be accurate. I assume they are just as accurate as my model was. One is that my model do the same thing for those samples. Those samples are not going to, I mean, they're representative of the previous tasks, but they're few. And as long as I get the same performance for those images specifically, I assume that my parameters haven't changed much. So I get the same performance across all the samples in that task. But it really doesn't matter if the saliency maps are incorrect, are inaccurate.
Okay. And the second question would be, Is there any reason why you chose L1 loss or not
I
L1?
tried L2. I tried L2. It really didn't make any difference. Slightly L1 was better.
Ah, okay. But you're not trying to enforce some kind of sparsity or something like this?
No, I didn't try anything. I mean, it worked as it was. Yeah,
okay.
I didn't go for more. Yeah, but you can definitely do.
Okay, thanks.
Sure, thank you.
Any other questions?
Yeah, I have a question.
Go ahead.
Do you think this could be used in some way in like different settings instead of class incremental settings in like online stream settings? Could there be a way?
Yeah, I don't see any reason for that to not be the case. Yes, you can use it for the online setting as well. All you need to do is just keep a saliency map along with the images you store if you're doing an online method that stores samples. Or even if you're not going to play those samples in the replay buffer, so the model is not going to see the raw data, you still can use the explanations. But that's a little bit weird. I mean, if you have the samples from the past, you might as well replay those for the model. That always helps. Yeah.
All right. Thank you, Sayna, for joining us today, and thank you all for this great discussion. I invite Sanya to send me the slides of these talks so that I can upload them on our forum where we can continue the discussion. And I invite you all to join next week, next Friday, the ContinualAI meetup that is going to be on benchmarks and evaluations for continual learning. So thank you all, guys, and see you then. Bye.
Thank you, everyone. Thanks. Bye.